Hello everyone, my name is Huang and I come from the Australian National University. In this presentation, I'm going to talk about the effect of battery storage participation in Australian wholesale electricity and frequency control markets. I will first introduce the background and the Australian electricity market. Then I will explain our bidding models and experiments. The conclusions will also be summarized. The motivation of our paper is that there continues to be an increasing adoption of battery into the power system. Take Australia as an example. We can see from this graph, the amount of fossil fuel generation keeps decreasing while the penetration of renewable energy is expected to increase. This means there's a lot of interest in firming capacity, which can be provided by batteries. Therefore, we should carefully consider how these batteries operate within the market and the effect they will have. Now, let's look at how current market works. The mechanism of the Australian national electricity market is similar to other spot markets around the world. It's dispatched on a 5-minute loading horizon. All participants in the market are required to provide price quantity pairs at their bids. For example, this means a generator is willing to sell 30 megawatts of power at $5 per megawatt hour. As this graph shows, all generators bid to sell electricity, then produce the supply curve. At the same time, all scheduled loads also bid to buy electricity, then produce the demand curve. The intersection of these two curves is the market clearing price. As for a battery, it can bid as either a generator or a load. Hence, we need to consider how to generate the battery's bids. The most straightforward way is to act as a price taker, which means the battery would not influence the market price. As this graph shows, we optimize the battery operation by maximizing its profit based on price forecasts. As a result, it would charge at lower price than discharge at higher price. The bids of the price taker model are then formulated from the optimization result at the first interval. If the result is discharging, then battery bids as a generator at price floor. If the result is charging, then battery bids as a load at price cap. The model will bid the optimized capacity where optimization relies on predict price, but bids are formulated to accept any price. These figures illustrate the battery behaviors and market prices after using a price take model. The purple lines show the original prices, where the blue lines represent the prices after battery participation. For a small battery, market prices are not affected, and the price taker model is therefore a valid bidding strategy. However, for a large battery, the price taker model breaks down with the price reaching a price cap and floor on many occasions. Therefore, as the amount of batteries in the market increase, the batteries will begin to influence market prices. At high enough penetrations, the price take model is no longer a sensible model for battery bidding. A more realistic bidding model should attempt to only submit cost-reflective bids that will always result in profitable operation of the battery. Here we describe our procedure for generating these bids. The first thing is to generate a list of price scenarios. Here are two examples. The price of the first interval are different for different scenarios, while the rest intervals remain the same. The next step is to determine the corresponding bidding quantity. We optimize the battery operation for each price scenario and obtain the result at the first interval as the bidding quantity. These figures show the battery operation results with our cost-effective model. Compared to the plastic model where large batteries result in market disruption, we can see our cost-effective strategy experience less fluctuation, especially in the case of a large battery. The participation of the battery is observed to reduce some price specs, which is a clearly desirable outcome. So our cost-effective bidding strategy can make rational decisions that preserve battery revenue and allow the market to function in a reasonable manner. In addition, we have calculated some metrics to evaluate the performance of our bidding models. The first one is the average market price. As shown in this graph, with the increase of battery size, the price taker leads to price disruption and market breakdown for battery penetration of around 400 megawatt-hour. But the cost-reflective model reduces the volatility to a large extent. The impact of high battery penetration on the market can also be observed when considering battery revenue. This graph shows that the revenue of the plastic model decreases with the growth of battery size and reduced to negative when the battery is large enough to disrupt prices. The batteries with cost-reflective model achieve positive revenue even at large battery size. As a consequence, our cost-reflective model is an effective bidding strategy for battery participation in the market. In conclusion, taking Australia's market as an example, we developed a cost-reflective bidding strategy. Our experiments indicate that compared to a price taker, using the cost-reflective model improves price stability while maintaining a positive revenue even for large levels of battery penetration. That's all. Thank you for listening.